The part 3 notes where we're going to talk about the difference between purely covalent and polar covalent molecules. Okay? In a purely covalent molecule or purely covalent bond, I have equal sharing of my electrons. I have these backwards. It's okay. So over here, O2, HCl, obviously. So I'll draw Lewis dot structures to show this. Kind of separate these two. So I know that when that diatomic oxygen forms a double bond with itself, and each oxygen is left with 2 lone pairs. Okay? My shared electrons are in the center, in the bond. And because oxygen is bonded to itself, they have the same electronegativity, the same pull, the same attraction for electrons. Because of that, I have a nonpolar bond and a nonpolar molecule. The electrons are equally shared between the oxygens. Okay? As opposed to, and in regards to this purely covalent, you also might call this nonpolar. Your book calls it purely covalent. You may hear it outside of this class referred to as nonpolar, or by me as nonpolar. When I look at polar covalent, I have unequal sharing. I create poles. Unequal sharing. Specifically talking about electrons here. So hydrochloric acid, we've talked about this. We drew it earlier actually when we were doing shapes. Hydrogen bonds to chlorine. And what I find here is that I have unequal sharing of electrons. Okay, chlorine is much more electronegative than hydrogen. We're talking about electronegativity, if I can write. Chlorine is more electronegative than hydrogen. Remember, I showed that we talked about periodic trends in Module 8, and we said that fluorine is most electronegative. Electronegativity, I'll actually pull my periodic table. We said that fluorine was most electronegative. Electronegativity increases as you move across the periodic table, decreases as you move down the periodic table. So with hydrogen being completely on the other side over here, much less electronegative than fluorine. Okay. So when I draw this bond out, if I want to show that polarity, I can do it like so. Instead of just drawing the bond, I'll show that the electrons are more pulled towards the chlorine. So here I have a polar bond. They're not equally shared in the bond. And I have a polar molecule. I'm more likely to find electrons over here by chlorine than I am beside the hydrogen. And the way I represent that looks like so. I'll show hydrogen bonded to chlorine. And then I'll draw this little, I don't remember what Greek letter this is, it's getting late at night, with a negative charge. That means that that's the negative pole of this molecule and the positive on this other end, okay? look it up really quick. So that's a delta, lowercase delta. Okay, so delta positive or delta negative on your more electronegative side, delta positive on your less electronegative side. Okay, and that arrow points towards your more electronegative. More electronegative atom, really. Okay, pretty straightforward. So, do some practice here. Talk about CF4. This one's going to be a little trickier than the examples we've shown. So, I know that carbon bonds, each fluorine, if it's CF4, this is a basic one. And I know that each fluorine has 6 electrons around it in addition to the bond to carbon. We know that fluorine is most electronegative, so of course my electrons are moving towards my fluorine in each of these bonds. Okay, so these are polar bonds, all of them, because my electrons move towards the more electronegative fluorine. However, this is a nonpolar molecule. Why? That's a great question, Ms. Hanley. So think back to the last video. We talked about molecular geometry. This is an AX4 tetrahedral shape. Despite the fact that my bonds are pulling my electrons towards my fluorine, they're pulling out in equal but opposite directions. So those pulls cancel each other out. Okay, so each bond is polar, but overall the molecule is not polar. Okay, so ultimately, what is that, based on what I've learned so far, what does that tell me? In order to have a polar molecule, I have to first have polar bonds. We've seen that. But I also have to have unequal pulls. Okay, so quick hint. If lone pairs are present on that center atom, it's a polar molecule. Okay, that's a helpful hint. Now, I'm going to flip this page over because I'm saving paper, I guess, and we're going to do a couple more examples. Okay, are we where you can see this? Okay, maybe not. Okay, we'll do water. And I think you all already know this about water. I draw my water molecule. I know water is bent. Remember, AX2E2, meaning center atom bonded to 2 atoms with 2 lone pairs on that center atom. Oxygen bonded to hydrogen, with 2 lone pairs on the center atom. Oxygen is definitely more electronegative than hydrogen. Hydrogen is so little electronegative, least electronegative. Okay, maybe not least, but very low electronegativity. So if my electrons are being pulled towards the oxygen and they're in this shape, my pulls are not in opposite directions, so they will not cancel each other out. So I'll draw the molecule again. And I'll end up with a negative pull on this end and a positive pull on this end towards the hydrogens. Okay, so I have polar bonds and a polar molecule. Okay, polar bonds, polar molecule, because the poles are not in opposite directions. Okay, really quick, some information about polar molecules, some properties. Polar molecules can dissolve other polar molecules. We know a lot of things dissolve in water, so that makes sense, right? Water is a polar molecule, so it can dissolve other polar molecules. Can also dissolve ionic compounds. This makes sense because ionic compounds don't share electrons. One takes, one gives, creating that electrical charge where one thing's positively charged, one thing's negatively charged. Okay, there's a way to draw this out, but it's a little confusing. Just know that polar molecules can dissolve other polar molecules and ionic compounds. And then those purely covalent molecules or nonpolar can only dissolve other nonpolar molecules. Okay? Pretty straightforward. And the general term for this polar can dissolve polar, nonpolar can dissolve nonpolar is like dissolves like. So things that are alike can dissolve, alike can dissolve each other. Okay? We'll do a few examples here. Like dissolves like. Sorry guys, I didn't move the camera down. If you're still writing, I'll move it back up real quick. Okay, even though I guess you can pause the video. Okay, another example. We will do SO3, my sulfite ion. For those of you who remember from Monday, I'll draw it out, SO3 with a -2 charge. I end up with sulfur double bonded to an oxygen, bonded to an oxygen, bonded to an oxygen. If you need to draw these out from the beginning, by all means, go ahead. And in the case of sulfur and oxygen, I'm actually going to pull my periodic table out so we can see it really quick. Oxygen is more electronegative than sulfur. Okay, remember, electronegativity goes down as you move down the periodic table. So oxygen being higher means it's more electronegative than sulfur. Okay, so that means my electrons are going to move towards my oxygens. Okay, this is that AX3 geometry we covered, which is trigonal or trigonal planar. Okay, do I have polar bonds or not? Yes, I have polar bonds. Do I have a polar molecule? And this one gets a little bit tricky because I have things pulling in 3 different directions. But if you were to work out the X and Y pulls of each of these, you would end up canceling each other out. So this is a nonpolar molecule. I'll try not to trick you on your test with something like this. Okay? And so on your test, you would have a question like, draw the Lewis dot structure for this, state the shape, and then will it dissolve in water? So something like this. This is a nonpolar molecule, so no, it will not dissolve in water. So dissolve in water. And I know there are questions in your on your owns like that as well. Dissolve in water? No. Why? Because it's a nonpolar molecule. Okay, two more. NH3. We've drawn this one many times. Nitrogen bonds hydrogen. And remember my little trick we wrote on the other page. If you have lone pairs on the central atom, you have a polar molecule. Yeah, you'll find that to be true. Okay, nitrogen's more electronegative. If you need something to show you the electronegativity, just to be sure, Google electronegativity table. I'll try to link one when I put the assignment together for this. But if I don't, just Google it. Okay, so polar bonds. I'll go back and write the shape too. I have center atom bonded to 3 atoms, so AX3, and I have one lone pair on my center atom, so that's AX3E. So that makes my shape pyramidal. And we actually did this one earlier when we were doing shapes. Okay, so if my electrons are pulled towards my nitrogen, think about that shape when we saw it in the 3D, where this is almost like a tripod with the lone pair on top. That makes this a polar molecule. Okay, can draw that like so. My electrons are more towards the nitrogen, less towards the hydrogens. So I end up with that partial negative, partial positive based on that. Okay, polar molecule. Will it dissolve in water? It's a polar molecule, so yes. Okay, and then one more example. We'll do NH4, the ammonium ion, which we covered when we covered polyatomic ions on Monday. So, similarly, nitrogen bonds each hydrogen. And remember, we have some 3D geometry going on here, but this is AX4, center atom bonded to 4 atoms. So this is a tetrahedral shape. Nitrogen is more electronegative than hydrogen. We just said that with the last one. I'm drawing this one the wrong way, sorry. Okay, so I have polar bonds. In most cases, you're going to have polar bonds unless you have two of the same element. There's some things that fall where their electronegativity will be really similar, but for the most part, if it's not the same thing, you're going to have a polar bond. Is this a polar molecule? Equal but opposite poles makes it a non-polar molecule. Okay, can I dissolve it in water? No, because it's a non-polar molecule. Okay, and that's really all to know there. Use an electronegativity table to be able to determine if you have a polar bond, which direction it's pulling, and if those pulls will cancel each other out to determine whether your molecule is polar or nonpolar. If you have a polar molecule, it will dissolve in water. If you have a nonpolar molecule, it will not. Okay? Message me with questions.